it was this. We had one battery on a circuit over here, and we had wires connecting it up, and there were points labeled 1, 2, and 3. And we had the same battery over here with wires, this was the positive, this was the positive over there. And we had wires coming out like this, and like this, and we had these points labeled 4, 5, 6, and 7, and we wanted to determine how those currents were related. The length of all those loops were the same size. Yeah. I'll remind you, I don't want to repeat the question. I don't remember it. I'll remind you the answer was that 1, 2, 3, 5, and 6 were all equal, and 4 and 7 were equal but bigger than those ones. And then we're going to go over why that is. That's what we're going to get. I want to try and convince you that we can set up equipment and do it, and I can prove these aren't right, but I want to try and convince you why that's going to be correct. Any other questions? Okay. This is going to be the basic answer to all this. I'm going to give you the statement I'm trying to get you down. Maybe some of you got the understand right away. Batteries do not control directly the current in the circuit. Batteries only control the potential difference, and everything else controls how fast the charge is moving. We're going to spend the next 20 minutes explaining that statement, so I want you to listen to it right now. I'll say it one more time. We're going to spend the rest of that explaining it. Batteries do not control the speed of the charges directly. If you have a bigger battery, the charges will go faster. But the battery itself doesn't control how fast the charges go. Battery only controls the potential difference. The rest of the circuit will affect how fast it goes. We'll talk about that in a while. Now, let's first, so some people said they were confused about some of the words in this chapter. So let's try and discuss some of these words. The first word we should talk about here would be the word current. Current. Can someone give me a very brief explanation of this? 12 electrons, positive charge, Dominic?
Are we going to talk about potential difference too?
Yeah. I'm looking for one more. It's 12 electrons. We talk about the positive charges moving. That's really by definition. When we say flow, what do we typically mean by the word flow? Different S word. Speed. Good. The current is the speed of the charge moving through the circuit. Not necessarily of the individual charges that are moving, but the overall flow, the speed of the charge, or the speed of the charge, the speed of that domino effect as it goes through the circuit. Do we have an equation for current? Well, that's Ohm's law. That's also for current, but there's another one that we have. That's one equation for current. Good. The current, the definition of current is it's the number of charges, Q, the change in charge, the triangle, sorry that, over the time at a certain point. And so, for example, if you had a wire you were watching, and you had X-ray vision, and you could see the charges, here's you looking at the wire, and you were to count, say, 1, 2, 3 coulombs that passed you in 1 second, you have a charge or a current of 3 coulombs per second, which would be equivalent to 3 amperes of current. So, going over our letters, I stands for current. Originally, from what I've read, I is the current and the brightness of a bulb are going to be essentially the same thing. If you have more brightness, there's more current. So originally they called current intensity. That's where the I comes from. And we can't use a C, because what things do C stand for in physics? There's a couple of dimensions. Coulomb can be very confusing. What else?
Constant.
What's that? But you have to be sure.
Sometimes
Celsius would be another one. The speed of light is denoted by the letter C. And of course, C stands for cookie. And so we don't want to have all those different things that means C. So we leave current as I. Okay? Q stands for charge. Again, if we use the C for charge, that would be confusing with the units of charge instead of coulomb. It sort of adds up with voltage and volts, right? We want to have charge and coulomb to be the same letter. So Q is our symbol for charge. I don't really know why, other than Q is not really much else. Then T obviously is time. So the current measured in amps or amperes, names for a French guy, are the number of coulombs that pass you in a second. That's current. This is how fast the charges are moving. Okay? Woo. So next, we're talking about what Dominic want to talk about. That is potential difference. Potential difference is probably the topic in physics I've had the most trouble with. I've spent hours reading and talking about this stupid topic, and I kind of hate things different. It's not stupid. It's just, for some reason, my brain is that stupid. And so I will tell you what I think I know about it, and we'll find out. So, potential difference. This is what we're talking about if we refer to it as voltage. We want to try to avoid referring to it as volts. We don't want to refer to things as a unit. But voltage is different than saying volt. Potential difference is often referred to as the voltage. And so, anyone have an idea what potential difference is, or what you can describe it as? Where does it come from? Matt? Okay, good. So potential difference we're going to equate very closely with energy. And so potential difference is telling me that there's a difference in energy between two different places. And we're going to talk in a minute here about mountains and hills. And we'll talk about again that if you're on top of the hill, you have a certain amount of energy. If you come down the hill, you have a change in energy. That's essentially what a battery is doing. It's setting up a hill that an electron has to climb. And the bigger that hill, the more electron has to do to get to the top of that hill. We talked about, I think, that the potential difference we're going to measure is something called a volt. And a volt is equal to a joule. What's the joule stand for? What kind of unit or what kind of thing is a joule? Energy. So a volt is a joule divided by a coulomb. So a volt, or this potential difference idea, is trying to give me some kind of term that talks about the energy we're going to store a charge if you move it, but they're trying to give you a term that applies to every charge. And so if I know a battery has a 3 volt potential difference, then if I had a 1 coulomb charge, it would gain 3 joules going through that battery, or from that battery. And so that's why we can say voltage and energy are really almost the same thing. Voltage is just trying to be a term that doesn't rely on the charge to get the value. Potential difference. And this is what gives energy to the circuit. Potential difference gives the circuit energy, and it causes the charges to move. Essentially, the force that pushes the energy, pushes the charges through the circuit. Okay. So, how are these 3 things related? That's an excellent question. I'm glad you asked that. Let's talk about a mountain. I like talking about mountains because you guys understand mountains. You understand the energy involved with mountains, all those other big things. So we're going to try to discuss it in terms of mountains because, like I said, you guys understand that. And maybe if we can draw the parallel between those two, it'll work out well for us. What's up? Oh, yeah. That was cute. Yeah, I can see that.
Why is this screen like fully?
Don't worry about it.
All right. I won't.
I'm going to ask you the bear for it. Bear is the one day. It's something you don't learn.
Jeff said you're trying to
It's actually it's a cerebral pulse that makes it so that all the distracting tendencies you have focus on the board. So let's say we had a mountain that was 1.5